In this example, we want to look at the set of positive real numbers with an unusual addition and scalar multiplication and show that that space is actually a vector space. So let's first write down what we know. We have that V is the set of positive real numbers, so that this is the set of x and r, say, such that x is greater than 0. And addition is defined by taking two vectors in our vector space V, and when we add them, we get x plus y by definition is equal to x times y, and I'm just removing the vector notation here because they're just real numbers. And scalar multiplication is defined by taking some real number and some vector in V, and we get that k times x by definition is equal to x to the power k. Again, I'm removing the vector notation since x is a real number. To show that V with the given addition and scalar multiplication is a vector space, we have to show that axioms A1 through A5, the addition axioms, and S1 through S5, the scalar multiplication axioms, hold for this space. So let's check the axioms. And keep in mind that most of these follow quite readily by the properties of real numbers. Axiom A1 requires us taking two elements of our vector space and showing that it is closed under addition. That is, when we take two positive real numbers and add them, do we get a positive real number? But by definition, x plus y is equal to x times y, and this is a positive real number since x and y are greater than 0. For A2, we have to show addition is commutative. So let's take two elements of our vector space. So when we add them, by definition, we get that x plus y is equal to x times y. And since the order of multiplication of real numbers doesn't matter, this is the same thing as y times x. And unwinding the definition of our addition then gives us the vector y plus the vector x. Again, what's important is just remembering that this holds by the properties of real numbers. That is, order of multiplication doesn't matter in real numbers. For A3, we need to show associativity. So let's take three elements in V, so three positive real numbers, and let's show that when we add x to y plus z, so we're doing y plus z first, we get that this is the same thing as doing x plus y first and then adding z. Well, again, let's just use the definition. This is the same thing as x plus y times z, which again, by definition, is equal to x times yz. And since the order of multiplication doesn't matter in real numbers, we can write this as x times y first, then z, and then again, unwinding the definition of addition gives us as x plus y in parentheses plus z. So A4 requires a little bit of thinking. We want a zero vector. So we want 0 such that when I take any element of my vector space and add it to the 0 vector, I get my element back. So when you do the addition 0 plus v for any v in our vector space, look at it by definition. This is the same thing as 0 times v, and we want this to equal v. So what does 0 have to be in order for us to get our element back? Well, that means that our 0 vector necessarily needs to be 1. So we've shown that there exists an element in our space, the 0 vector, such that when we add it to any other vector, say v in our space, we get v back. And commutativity follows by axiom 2. Axiom 5 also requires a little bit of thinking. So let's take some element x in our set V, and we want a negative x such that when we add x plus negative x, we get the 0 vector back. Again, let's go by definition. This is saying when I take x and multiply it by something, I have to get 1 since 1 is our 0 vector. So that necessarily means that our negative x needs to be 1 over x. So we've shown that for any x in our set V, there is a negative x, such that when we add those two quantities, we get the zero vector back. So for the addition axioms, it's just A4 and A5 that require a little bit of thinking. Let's quickly go over the scalar multiplication axioms. So for S1, we take an element of our space, so a positive real number, and k is any real number. And when we multiply k times x, by definition, this is x to the power k, which necessarily is a positive real number since x is positive. So we're looking at an exponential with a positive base. For S2, we take two elements in our space V, and we take a scalar and show the distributive property. So we consider k times x plus y, which is equal to, by definition, k times xy, where here this is ordinary real number multiplication, and over here we have our new multiplication, our scalar multiplication. So using our scalar multiplication definition, this is the same thing as xy to the power k in real numbers. So using properties of exponents, this is x to the k, y to the k, which we break up with our addition in our space as x to the k plus y to the k. So this follows by addition in V. And then using our scalar multiplication in V, this is the same thing as k times x plus k times y. So again, this is by the scalar multiplication in V. For S3, we take two real numbers, so let's say k and l and r, and an element of V. And we need to show the distributive properties over the real numbers. So let's consider k plus l times x, which by definition is x to the power k plus l. Using the rules of exponents, this is x to the k times x to the l. And breaking this up using the addition in V, we get x to the k plus x to the l. And then using the definition of scalar multiplication, this is k times x plus l times x. So again, this is by scalar multiplication in V. This is by properties of exponents, real numbers. This is addition in V. And this is, again, scalar multiplication in V. S4 requires associativity of our real numbers. So let's again take k and l real numbers and x in V. Then k times lx is equal to lx to the power k, which is equal to x to the l k, which equals x to the lk, properties of exponents. And then reversing the process, this is now lk by definition of scalar multiplication times the vector x. So let's just reiterate, this follows by scalar multiplication in V, this follows by scalar multiplication in V, this is by properties of exponents, and this follows by scalar multiplication in V. And finally, we have to show that if we take any element of our set V, so any positive real number, and the number 1, so the real number 1, when we multiply 1 times x, we should get x back. Well, this follows since 1 times x is equal to x to the power 1, which is just equal to x, our original vector in V. So although it took some work, we've shown that the set of positive real numbers with the unusual vector addition and scalar multiplication is a vector space.